Memory of Herbert draws. We begin with a mini silent in memory of Herbert draws. Please stand up. I give immediately the word to Esther Rose because her health situation is not ideal and he has to go away as soon as possible.
Ich spreche nicht Englisch,
Wie du willst, Esther.
Gut, ich spreche Deutsch, weil die meisten verstehen. Ich bin sehr erfreut und auch berührt, dass ihr wiedergekommen seid, nach 30 Jahren, nach Herbert zu diesem Treffen. Und ich bin auch sehr erfreut, dass ihr immer noch Freude habt und Lust in dieses schwierige Gebiet, das Herbert eröffnet hat, wiederum einzutauchen und dass ihr ja schon eingetaucht seid, ganz am Anfang mit der Dissertation. Ich danke euch, dass ihr gekommen seid. Ein ganz großer Dank geht an Remo, der schon vor einem Jahr begonnen hat mit den Vorbereitungen und der keine Mühe gescheut hat, um dieses Treffen möglich zu machen. Es war diesmal nicht einfach, weil all die Sponsoren waren nicht mehr gewillt, wie früher Geld freizumachen. So ein Mathematiker-Treffen. Die haben alle das Gespenst der Krise vor Augen. Ich danke auch. Aber Remo hat es möglich gemacht. Ich danke auch Aldo, der auch noch geholfen hat am Schluss mit der Realisierung der Atti bei technischen Problemen. Und ich danke Suzu, der sofort gesagt hat zu mir, weil er weiß, wie wichtig mir meine Vergangenheit ist und wie sehr ich mich auf das Treffen mit euch gefreut habe. Er wolle es filmen. Schauen wir dann, wie es herauskommt. Er hat ein bisschen eine komplizierte Apparatur. Was mich anbelangt, ich hätte euch sehr gerne wieder eingeladen zu uns und hätte mich sehr gefreut, wieder zu kochen, so wie das die Tradition ist. Aber es geht diesmal nicht, weil es mir einfach nicht möglich wäre, so lange in der Küche zu stehen, nach dieser misslungenen Operation. Jetzt wünsche ich euch eine spannende Reise in die verschiedenen Gebiete eurer Vorträge und freue mich, euch heute Abend und morgen Mittag wiederzusehen. Ich hoffe sehr, dass ihr möglichst alle morgen Mittag dabei seid.
Ja, okay. Prima. Dann.
So we have the honor to give
the word to Hans Keller. I remember that Hans Keller worked very close to Herbert Ross, and he was the first in the planetary history to discover an example of non-classical Hilbert space. So, thank you very much that you are here, Hans. I give the word to you.
To begin with, let me say that I'm glad to stay again here in Locarno. Our last meeting in Memoria di Herbert was 10 years ago, and so I'm pleased to see you again and to have the opportunity to learn what I have done and present myself some mathematical results. In the work of Herbert Ross, the modular spaces are a central line of investigation, and it's a topic which was also in the center of my modest efforts over the last decades. My work was done in collaboration first with Appenzeller, and in the last 10 years, above all with Elena Olivos. So what I present has grown out of joint work over that time. Well, not forget to express my thanks to the organizer of this meeting, is the host, Aldo, and above all Remo, who has done a hard work to make it possible and who has struggled against very kinds of obstacles here. So clearly, I appreciate that very much. The topic is the composition of matrices over fields of power theories. It's not so obvious that this topic has much to do with orthomodular law, but it has grown out of studies of orthomodular spaces. So I begin by repeating or by looking at that orthomodular spaces. There will be, that's what I first do. There is some repetition of what Elena has already explained. Then I shall describe the setting in which we move the fields and the matrices, and then the central point is orthogonal compositions of the matrices, and can state the main result, and I'll give a computation what to do. At the end, a short outlook of what is ahead, what we are concerned with actually. Well, the theory of orthomodular spaces it's grown out of studies on classical Hilbert spaces, and these spaces are prominent topic in the mathematical theory, and are particularly important because of the relation with mathematical theory of quantum mechanics. Just very shortly, how does this work? Physical system is associated to a complex Hilbert space, and observables, that can be energy or position and so on, are given by permission operators. Now, in the attempt to reconstruct the theory axiomatically, most the starting point are, there are many treaties on that. The starting point are so-called questions that are elementary properties which can be detected by the so-called yes, no experiments. The experiments that have only two possible answers. Simple example, if you take a region into space and you ask if such a particle can be found in that region, yes or no, and from that elementary properties, the art is to reconstruct the theory, and then the state of the system is this can be described by boundaries, linear operators which are self-adjoint, must be positive and of trade. But in all that axiomatic reconstruction, there are some unsatisfactory aspects. The question why heap of spaces. And the first answer is clear that the crucial property of complex Hilbert spaces, as pointed out by Elena, the projection theory, which states that topologically closed subspace belongs to every subspace. There belongs an orthogonal projection. Now, another main property that topologically closed subspaces are orthogonally closed, which allows us to state the projection theorem in a purely algebraic form. And now we can go to, this is equivalent to the fact that the lattice of all orthogonally closed subspaces satisfies the modular space. That's where the name comes from. Also, these spaces first were non-classical Hilbert space or modular spaces. I think there are even other names given to it. Now we can even abstract definition of the modular space is an inner product. A vector space with an inner product, and we say it's orthomodular if the law even there is satisfied. And the problem is finite dimension, clearly that's easy to see which basis in finite dimension satisfies asymptotic. That's not interesting. In infinite dimension, it's much harder to find examples. And that's non-classical examples, as Remo has pointed out, just some essential features of it. They are constructed over certain non-Archimedean value complete fields. Here, the valuation is to a group gamma of infinite rank. And E is a sequence space, no surprise, and there is an inner product on E, and which gives rise to a non-Archimedean norm, I obviously set it. Well, if that goes in the direction of Elena, the norm, the values of the norm are not true. We have to use the two closure or the divisible power is too large, but if the two divisible power is sufficient, but that's not essential. Here, the point is that the C space The main probability property that clause is the same if we take it orthogonally or if we take it orthogonally. And then that a clause, linear subspace, gives also rise to orthogonal decomposition, which is equivalent to the fact that there is an orthogonal projection from the root.
Excuse me, can we make it a bit larger possible?
Yeah.
Größer machen ein bisschen. Das Bild vergrößern, geht das? Ich sehe fast nicht.
Wie kann man das vergrößern?
Was ist das für ein Software?
Das ist ein PDF.
Mit Scroll, Control und Scroll. Das braucht ich fast nicht raus.
Ich habe einen daheim. Ich habe einen im Zimmer. Gleich so.
Das bringt den Maus zu. Das Auto mit der Glas.
Was bringt das?
Ja, sicher.
Ist schon besser?
Ah, schon besser.
Ah, prima.
Applaus, Ben.
Ist besser.
Grazie.
Dabei habe ich im Text, im Latex-File extra auf Großbuchstaben umgestellt, aber ich fand es immer klein.
Nein,
Ja.
alles erwähnt.
I said that value group has infinite rank, which means that there is an infinite chain of isolated or convex subgroups, and to every such subgroup there belongs a valuation ring and with maximum idea and and consequently a residue field and residual spaces over the residue field. And now that is that the fact here in the standard example of orthomodular space, turns out that the residue field is a field of power fields in infinitely many variables. Infinitely many variables. And the residue field is finite dimensional. Important, a bounded linear operator induces a linear operator on the residue field. And this method of reduction turns out to be a powerful tool. In our study after the year 90, so with Herbert, with Armenia Oxenius, we first focused on a study of the algebra of bounded linear operators. And then that's a feature which is missing in the classical theory. There are no residue fields. But here we have that method of reduction, and which provides very useful information about the large operator. So this brought us to study finite dimensional spaces, operators, or equivalent matrices. And that's how we came to the topic of matrices of finite or finite size over fields of power series, but only with a finite number of variables. It seems at first that should not be too difficult. We are in finite dimension, we have induction, and the fields here are arithmetically easy to handle. You can easily detect if an element is a square or not, and to solve equations should not be too difficult. Nevertheless, there arise problems and difficulties. That will, even in the simplest case, and that's what I will do here. I have to go back. I concentrate on fields in just one variable and with real coefficients. The elements have the form of power theory, which starts at some point, and the starting points are known, the index of the starting point, that will be the value of that element. Here, valuation treated additively and often here we can switch to multiplicative. I should have a mouse. Yes. So there we switch in the usual way to a multiplicative valuation. It's non-Archimedean, has rank 1, and the field is spherical complete. And an additional property which is important, that the value of sum of two squares is equal to the maximum. In the general theory, it's only less or equal, but here we have equality. Then we consider the ring of all matrices of size n times n over that field K. Here they look as indicated here. And as usual, I will put A star for the transpose, for the E and for the IN for the unit matrix, and A is called symmetric if the transpose equals A, and we say it's orthogonal if A asterisk times A is, or if the transpose is equal to the inverse, that's the same thing. And what's our sample problem? First, let us call two matrices orthogonally similar if one can be transformed into other by conjugation by an orthogonal matrix. Here the point is the transformation matrix U must be orthogonal. That's what we require. And the task, if we have any matrix, to find an orthogonally similar matrix which is of simpler shape, whatever that means. But we have in mind certainly the classical results, that's the spectral theorem of symmetric and real matrix. As a result, the theorem states that any such matrix can be transformed into a diagonal matrix. And the first result was that theorem carries over to matrices of our present base field. It can also be put in a diagonal form by means of an orthogonal matrix indicated here. Well, that is also, if we have symmetric matrices, the answer is given by that. The simplest form you can imagine of a matrix is a matrix in diagonal form. But now I focus not on symmetric but on orthogonal matrices over these fields. And they cannot be diagonalized. That's easiest example, over the real numbers in dimension 2, a rotation matrix cannot be diagonalized, but that means it must have a base consisting of eigenvectors, which is certainly not the case. But we can try to get as close as possible to a diagonalization. That's what we try to do, is to decompose it, to find in this way that on the diagonal there are matrices of small sizes, and to push that process as far as possible. Again, some questions which arise here. We want to know conditions under which such a decomposition exists. If it is unique, or in what sense, strictly unique, we cannot expect it to be strictly unique, but in what sense? And above all, how are the indecomposable blocks in the diagonal? How do they look like? And the other thing, if we can compute the transition matrix and the blocks effectively. Well, that's what Let me mention that sometimes it's useful to adopt a geometric point of view on this problem. Here, the normal n-dimensional vector space over P and with the canonical base and the canonical product as given here. And then if we have a matrix of size n times n, multiplication from the left, that's a linear operator on the vector space. And it turns out to be an isometry if and only if that matrix is orthogonal. These are immediately elementary verification. And the possibility to decompose the matrix is equivalent to write the space as a sum of two invariant spaces as given here. If it has a linear subspace of dimension R, which is invariant under multiplication from the left, that's equivalent to decompose the matrix by means of an orthogonal matrix. This again is a very elementary fact and can be shown with a question of a few lines to verify this. So sometimes if we ask for blocks which are indecomposable, it's the same as to look for isometries which have no invariant subspace. And sometimes it's easier to look at it from algebraically or geometrically. That's Now, how can we attack such questions? The first important observation, if I have a matrix of size n times n with coefficient in that field of power series, and if the matrix is orthogonal, then all the entries must lie in the valuation. That's the absolute, the value is less equal than 1. But here exceptionally I thought my talk, I did not any don't enter into anything of proofs in details. I jump over all that, but here it's so simple that I give some indication. Simply to start with a defining relation of what is an orthogonal matrix, and then to look at some position in the diagonal. We obtain the equation given here. I mentioned, at least in mind, and I mentioned that basic property that the value of a sum of 2 squares is the maximum of the values, and that if it is true for 2, then it is also true for 12 or n summands, and so the claim follows immediately. Now, the coefficients are in the valuation rate. That's to say, the series starts with 0, or it's the right from 0. No negative powers are involved. And we express every entry of the matrix as such a power series, and then for each power of t, we collect the corresponding coefficients and put them in a matrix, which is now a matrix with real entries. And this gives a possibility to represent our matrices as power series in the variable t, but coefficients not numbers, but real matrices of the corresponding size. And this representation is at the heart of all reasonings that will come. Let me mention, we put skip that this, it gives a more conceptual way to look at the things. I mentioned the valuation ring, the maximum idea, the residue field, and the canonical homomorphism from the valuation ring to the residue field, which is the field of real numbers. Now, if we apply that reduction map to an element, clearly the result is the starting coefficient. If I apply the reduction map to the rule matrix, I just become, the result is the starting matrix A0. And this has a particular importance for computations. If I apply it to the defining relation, then we obtain that we see that A0, the starting matrix, is orthogonal. That's a real orthogonal matrix. And that will have an outstanding role. Now, again, what is our task? Given such an orthogonal matrix, we try to find an orthogonal matrix U such that U star AU matrix B is decomposed into two blocks of small size. In view of the above, we express all these matrices as power series with coefficients in the field of in the ring of real matrices. Just the first power, the constant term, shows us that the U star decomposes the initial matrix of A into two blocks of the same size. But we can obtain it by the reduction map, that's more conceptual. You can simply insert all that in the defining relation and to put T0 or something like that is a that's an easy thing. But now, what is our situation? If we have an orthogonal decomposition of the matrix R set in the large, over the large field, then the reduction map gives the corresponding decomposition of the initial matrix. Our concern is to go in the inverse direction. If we have an orthogonal decomposition of the initial matrix downwards, how can we go upwards and to obtain an orthogonal decomposition of the large matrix? Now, before examining the possibility of lifting such decomposition, let us have a look at the orthogonal of the corresponding task or problem in the case of real matrices. Here, the answer is quite clear, quite easy. It is convenient, I prefer to look at it geometrically to find if we have a finite dimensional real space and an isometry to find subspaces which are invariant for the isometry. It's strange, I think it's a simple, and there must be, I never came across results in that direction, but there must be folkloric knowledge about that. What we can say is, if the dimension is 3 or more, then there is always a proper subspace which is invariant under M. And if it's an isometry, then the orthogonal space is also invariant, and we have decomposition of space E into two invariant, or the matrix can be decomposed in two blocks. The case n equal 2 is special. In the real case, if it is a rotation with an angle not 0, not b, then E is indecomposable under that operation. And otherwise, it's a reflection, and it's then a sum of two invariant straight lines. And case n equal 1, clearly the isometry is plus minus identity. So, what we deduce from that, if we look at the space, we have two invariant subspaces, orthogonal one to the other, and then we consider the restriction. If the dimension is larger than 3, It must have other smaller invariant subspaces. We can decompose again. And finally, we arrive at the decomposition like this. Now I like to express it in terms of matrices. We have the part which is identity, another part, another block which is minus the identity, and then all what comes from two-dimensional invariant indecomposable spaces. These are rotations. That's to say, decomposition of the initial matrix is no problem, it's well known. Now I can state the main result. Here I consider orthogonal matrix expressed as power series with matrices with real coefficients. I suppose that the initial matrix has already been decomposed as indicated before. The critical point, I have to look at the rotations are the crucial thing. I have to look and to require that the rotations be, the angles of rotations are pairwise different. Omega g is different from plus minus omega k. And if that condition is satisfied, then we really can lift the decomposition of the initial matrix to the large matrix above. That's to say, we become decomposition like this, plus identity, or on the diagonal a certain number of plus 1, then on the diagonal a certain number of minus 1, and then some matrices of size 2, by 2, and they reduce the D reduced to the rotation matrices, and above there is identity matrices. That's the main result. Well, I announced that I would give some answer to how that works, the proof of that. Yes, later I give a computation proof, but let me mention that it can be, there is a shorter proof by algebraic reasoning. If you look at the characteristic polynomial of the large matrix A, that's a polynomial with coefficients in the field K of power series. And the problem is to that polynomial can be reduced by the reduction. Then you obtain a polynomial with real coefficients, and that's simply the characteristic polynomial of the initial matrix. Now the field is complete. So the polynomial is over the real numbers, so it decomposes in linear and quadratic factors. And then we can apply Hensel's lemma to lift that to a decomposition of the characteristic polynomial of the matrix A, provided here it fits with our requirements. But we ask that angles of rotation are different. And that ensures that the characteristic polynomials of these rotations are pairwise prime, relatively prime. And then we can apply Hensel's lemma to lift all to a decomposition of the characteristic polynomial, and that in turn gives rise to a decomposition of the space. They only mention that it's short of the proof, but it's claim that the computational proof is better or more efficient. We will see in the sense that it really computes the transition matrix. By that reasoning over Hensel's lemma, that is the existence, but I think it will be hard to get the effective decomposition from characteristic polynomial. But I try to give an outline of the proof. Not in general, it can easily be reduced to the path where the +1 and the -1 on the diagonal, that part of the matrix can be put away easily. That's no problem to do that. The more interesting is to lift the matrix where the two-dimensional the rotation matrix are there. And it is sufficient to consider the simplest case when the dimension is 4. The essential things appear in that case. So, in what can I suppose that we are in dimension 4, and the initial matrix has 2 rotations on the diagonal, and the angles are different. What we want is to construct the transition matrix. Clearly, it has the form as given before, a power theory with real matrices now of size 4 times 4. What are the requirements? It should be orthogonal, and it should decompose the matrix R into 2 blocks of size 2. Now, these conditions can easily be expressed in terms of the coefficient matrices, the U, G, and the A. It's just a question to insert and to compare powers of the variable T, and then the conditions are the following. The first is again orthogonality of the first, and well, from that on is a development of we must obtain zeros, and the important thing, the sum given here must be a block matrix. The problem is how to do with that. Clearly, we try to construct the matrices U recursively. We can start with the identity. More difficult or more to do is for the recursive step. So we suppose that we have found already these matrices until the number, and the first condition which we had, have to do again. The first condition clear here, the matrices with index less than n are known. But we try to find u n. So we separate the corresponding terms. And certainly from the sun, we take the un outside. And in that case, it means that, well, the second term, that's a symmetric matrix, already computed, and then u, the transpose plus u must be minus that symmetric part, so it means it's minus a half the sum plus, here comes something antisymmetric. That's the uncertainty or the liberty we have in that space, and it's important of that liberty. The next condition, that was with u, a, u, again, we make the same thing, two terms contain the variable or the unknown matrix un, and we separate it, and then we have a large sum on the other side, which remains, and that should not be zero, but a block. And what we already found, un is minus half Sn plus 2, we insert, and altogether, if we put, we arrive at this condition, that Qn star A0, but A is the n plus Mn must be a block matrix. Here, the important thing is that Mn is a part of its sum of things we already computed, but anything it's given. That is all what appears in the matrix Mn is known at this stage. Now the question is if we can meet that is the form, that's a crucial condition. We must meet that condition so we can complete the recursive step. And we look at it. We have to go downwards. These are 4 times 4 matrices. We have in the first to go down to the 2 times 2 blocks of the matrices. So we write this way the Q, N, and the M, and in this way, and we insert, and what we obtain, computing a little bit the real, which we see. The blocks on the diagonal don't matter. We only want it to be a block matrix, so we have terms on the upper right and on the down on the left. This must be 0. And so we get some condition. Now these are 2 times 2 matrices. Here I only deal with condition 5. Here. One in my written contribution, at the end of that, I simply claim that the condition can be dealt with similarly. In fact, my first version I wrote a general argument that which gives the same result. But Elena told me she did not understand well that argument, and she was not so confident that it is right. I still believe that it is right, but I try to convince her that it is correct. But here, to avoid difficulties, I simply mentions that. That's it. If you look at it, you will see that of. But now it's sufficient to. Again, we have to go one step downwards. These are 2 times 2 matrices. We write now with the coefficient. Then it's question to insert and to write out all the conditions. We arrive at a system of 4 linear equations for the x, y, right, and u are the unknown coefficients of the matrix P. On the other hand, the m, 1, 2, these are known elements or real numbers. And we arrive at a system of linear equations. The matrix of the system are here. Now, to solve it, we must be sure that the determinant is not 0. The case of determinant 0, then things may fail. Possibly we cannot solve with a degenerate system. So, determinant to compute it is good time. What we obtain is even here. Now, the first satisfactory point is that it is in agreement with our conditions we put at the beginning. Namely, if tau, omega and tau are equal, then the determinant is 0, because cosine of one and the other are equal. And there, that seems immediately that it is. So, point is that this case has been excluded if how it is in the other direction. If it is the only exception, that's what we need now to show. As a verification, it is not so difficult. If it is 0, then we put the difference of the cosines in the square as a new unknown, and we insert and we obtain a quadratic equation for u. And this quadratic equation, the discriminant is easily computed, and the solution is given here. Now, u is a square, so it must be non-negative. And we deduce that it is, here we have minus a square, so it can be 0 only, and then sinus tau must be plus minus sinus omega. And u still signifies that the cosines are equal, and that only can happen when tau is plus minus omega. And so we see that the condition we had to go back. Yes, that's an equation with a requirement 5 that can always be met or satisfied provided that the angles of rotations are equal. And with that clues, that's what we want. We can finish the recursive step and do the decomposition. So, in a summary, I give what is, again, if we are given an orthogonal matrix of size 4 times 4, then the initial matrix consists of two blocks of rotation matrices, and then the following procedure computes the orthogonal matrix of transition. We start with the identity, and in the recursive step, we first compute the matrix S, and then we introduce that matrix M, and we compute the 2 times 2 matrix Q from the equation given here. That's a 4 times 4 system of linear equations, so it should not be too difficult to do it. And then we put Q in the blocks on the diagonal. There is some liberty. The simplest thing is to put 0, but we could put another thing also. The matter, and finally UN is minus a half S plus Q. And so then it goes on. Let me first give a numeric example. Not too complicated. When I made it further, I was still working at Universidad de la Frontera when I had a mapping computer system at my disposition. That's no longer the case. So the matrix, well, now you have to develop it first to expand it. The coefficients must be expanded. There are not, there are in a field of power series, but there are 1 plus t square in the denominator, and so first we have to expand it, and then to find the coefficients matrix. I just give the first 4 up to A4. And then this question to follow the indications, what we had. Okay, look at the initial matrix. It is clear is on 2 blocks through rotation matrices, which clearly satisfy that condition of having different angles. And applying that algorithm, we obtain the matrices I computed it up to you see, if we remain in the field of fractions, it's not very useful to compute that much. We have to switch to numerical or decimal expansion or decimal representation of the numbers. My point here is that even with a calculator, it's not so hard to compute that's as shown in that design. Finally, an outlook. Well, let me first mention that the theorem deals with matrices over a field of power series in just one variable. It's easy to generalize to carried over to spheres of 2 or 5 or 6 or 7,000 variables. That's by induction on the number of variables. That's also. At the end, a glance at the exceptional case. There are two ones that E0 is d omega and d omega, or d omega and d minus omega. What happens in that case? Or what can we do or find out? Clearly, remember that's a well, then what we need, we have, the first thing is we have to, it must be an orthogonal matrix. And we have the same condition as we had for the matrix U. That must be the identity. And the next is n minus e must be 0. Here e runs from now, my matrix E0 certainly satisfies the condition. That's okay. The next one, if M1 is the condition. That must be 0. And the simple choice for the matrix E is the one I have been to. A1 this satisfies the condition. First I have to make sure that we can continue. That's again a lemma, which is both short time exercise in a course, an easy exercise to find matrices A2, A3, and so on, so that the resulting matrix A is all. Now, what I state as a theorem, if I begin with that A0 and that A1, then the resulting matrix is orthogonal indecomposable. Strange thing that it is indecomposable in a dimension 4. For the proof, I put some signs of interrogation here. For a long time, we were convinced that we had a strict formal proof of that. But recently, when I looked at it and for preparation of that talk, I realized that the proof had not a mistake, but it had a gain. But I'm sure that we can draw that gate there, that deficiency, I would say. But anyway, at the moment, I don't not produce a formal proof. But that's what we want to do, and then the aim is to understand geometrically what it means to be indecomposable. If that goes in dimension 4, we can, in the same way, obtain matrices of size 6 times 6 or 100 times 100, which are indecomposable as well. And that's a surprise for me. And it will be an outlook, a task, or the aim at that understanding of the matrix. Well, I think to show that there is still a lot of work ahead, and there are complications, complications when computing with matrices over these fields. So, in the next meeting I hope to have present more about these problems here. So thank you for your attention.
Bravo. Welcome to the third mathematical meeting in memory of Herbert Gross. We begin with a minute silent in memory of Herbert Gross. Please stand up.